right, so thank you guys all for coming back. So let me just recall where we stopped last time, right? So you know, when when you have a finitely generated group gamma, right? We talked a lot about. We spent a lot of time, some time saying what it means for this group to be hyperbolic, how to have this cos negative curvature on the group, okay? And using that, we can define the Gromov boundary of the group, okay? And we also define this flow space U gamma, right? Which admits a nice gamma action and a nice flow, okay? And the gamma action here is nice, meaning that if it acts properly discontinuous and co-compactly for one, and so you can look at the quotient gamma hat, which is U gamma quotient out by gamma, and the flow commutes with the gamma action, so it descends to a flow here. Okay, so this was what we talked about last time. Okay, so now we can finally get to our definition of Anosov representations. Okay, so this is via the boundary. Okay, so I'm going to first give a small, basically Labourie's original definition of what is an Anosov representation. Okay, and I'm going to do maybe a little bit of a controversial thing, which is I'm going to, for almost the rest of the mini course, right, I'm going to stick to the Lie group PGLDR. Okay, because I think, you know, sometimes, you know, when you work with semi-simple Lie groups in general, a lot of the formalism kind of obscures what is really going on. Okay, and if I just, even in the PGLDR setting, I think all the key ideas that I would like to present comes through anyway. So I'm going to stick to this Lie group. Okay, so I'm going to let G be PGLDR. Okay, and then gamma is going to be my hyperbolic group as usual. Okay, and then I'm going to let delta be the set of integers from 1 to d minus 1. Okay, so d minus 1 here is the rank of the Lie group. Secretly, these are the restricted simple roots of my Lie group. Okay, but for this purpose, I just think of them as integers. Okay, so now I'm going to fix some integer k instead of delta. Okay, and what I'm going to do next might seem a little bit unnatural, but just bear with me for now. Okay, so I'm going to suppose that I have a representation rho from gamma to PGLDR, right, admits a pair of rho equivariant, okay, rho equivariant continuous, oops, transverse maps, which I'm going to call CK and CD minus K. Okay, so these are maps from the boundary of gamma to the Grassmannians of K planes in RD times the Grassmannian of K, D minus K planes in RD. Okay, so transverse here just means, okay, so the CK is the one that ends up, that gives you a K plane, and CD minus K is the one that gives you a D minus K plane. And transverse just means that okay, let me write that down. Write it here. So transverse means that if you take a distinct pair of points in the boundary, okay, then if you look at the K plane given by X and the D minus K plane given by Y, okay, they have to span RD. Okay? All right, so let's just suppose that you have this first, okay? So what does this buy you? What it buys you is from this you can get a splitting of the trivial RD bundle over the flow space. Okay, so you have this, you can look at U gamma times RD, okay, over U gamma. Okay, so this is the trivial RD bundle over U gamma, and you have this splitting. So I'm going to call the splitting theta to the K plus C D minus K. Okay, so these are two sub-bundles of this trivial bundle. Okay, and what are they? Oops. okay, where this theta k, when you pick a vector v in the base, the fiber of theta k over this v is exactly ck of v plus. Okay, where this vector v, this is a vector in u gamma, is a triple, right? So it's v plus, v minus, and some time parameter t. So this is the forward and backward endpoints in the boundary of gamma. So I can evaluate it using my flag map ck. Okay, and similarly your cd minus k at v is this guy. Okay, so that gives you a splitting. So the fact that this pair of maps are continuous and transverse tells you that this is a continuous splitting everywhere. All right. Okay, and then once you have these two bundles, now you can build the homomorphism bundle between them. So I'm going to call that HK. So this is the space of homomorphisms from CD minus K to theta K. Okay, so this is a bundle over U gamma. Okay, and above any vector V here, the fiber is hom of CD minus K at V to theta K at V. Okay? So you have this hom bundle, and this guy now emits a gamma action. Okay, so what's this gamma action? Okay, if I take an element in gamma and I apply it to a pair, so I have a vector in the base and some f in the fiber. So this f here, this guy is in hom of CD minus K over V and to theta K over V. Okay, what is this? So on the base, you just apply the gamma action as usual. Okay, and on the fiber, what you do is you evaluate this element gamma using your representation. Okay, and then you conjugate this f by it. So this is rho gamma inverse compose f compose rho gamma. Okay, so when I write rho gamma here, what I'm really doing is I'm picking a linear representative of this projective transformation rho gamma. Okay, but this conjugate doesn't depend on the choice of linear representative. Okay, and this guy now is someone that lives inside of hom of CD minus K over gamma V theta K over gamma V. Okay, so you have this gamma action now. And this gamma action covers the gamma action on the base. Okay, and so you can quotient out by the gamma action to get a vector bundle now, which I'm going to call HK hat. So this is HK, quotient out by gamma. And then,
you have your inverse rule in place.
Yes, thank you very much.
Just in case it's confusing.
Yes, thank you, thank you. Sorry about that. Okay, inverse should be on the, yeah, okay. And over U gamma. Okay, so now we end up with a vector bundle over a compact space. Okay, now in this whole story you have flows everywhere. So remember on our U gamma we had a geodesic flow, right? Okay, so this geodesic flow leads to a flow on this trivial bundle as well. Okay, where you just flow in the first direction by the geodesic flow, and the second factor you just use the identity. Okay, I'm also going to call this guy phi t. All right. Now this flow leaves these two bundles invariant, right? Because if you see, when I flow here, right, I'm only changing the t parameter. The v minus and v plus do not change as I flow. So these things are invariant under the flow. Okay, so you have flows here, which you can restrict phi t to flows here, which I'm also going to denote by phi t. Okay, and then these two flows, they okay. So you also get a flow here. Okay, because as you flow, nothing is changing. Okay, so you have a flow on the hom bundle as well, which covers the flow down here. Okay, and you can verify that this flow here commutes with this gamma action, so the flow descends to a flow here. Okay, so what we end up with, okay, so in summary, if you assume your representation emits a pair of row equivalent continuous transverse maps CK and CD minus K, what you get is this vector bundle over a compact space with a flow that covers the geodesic flow here. Okay? Okay, so now we can make the definition of an Anosov representation. Maybe I'll push this all the way up. Okay, so definition. Okay, so a representation rho from gamma to PGL-DR is a PK Anosov. Okay, if the following conditions hold. Okay, so first, I want to be in the setup where I can do this. So I assume that, okay, let me use capital 1. There exists rho equivariant, okay, transverse, continuous pair of maps, CK, CD minus K, right, from the boundary of gamma to this product. Okay, so don't worry about what this, okay, so this PK here is what this, you should think of this as the stabilizer of the K-plane in RD generated by the first K standard basis vectors. Okay, so this GRKRD is G mod PK. Okay, so this kind of showed up in the previous talk today. Okay, so we have, so this is the first condition. Okay, so once you satisfy the first condition, you can do the construction that I just did over there. Okay, and then the second property that you need to have for this to be PK Anosov is a contraction property about this flow here. Okay, so for some, or equivalently for all continuous norms. Okay, on the bundle HK hat. Okay. There exist constants, big A, little a, larger than 0, such that what? Okay, such that, okay, so if you pick any vector V in the base of this bundle, okay, and you pick any element in the fiber above U gamma hat, okay, so in HK hat above V, okay, and you choose any positive time parameter t larger than 0. Okay, then if you look at F, right? So F is something that lives over the fiber of V. You flow it using your flow, phi t. You apply phi t to it. Okay, so now this is something above phi t V. You measure the norm there. Okay, and you require this to shrink exponentially with t. Okay. Okay, so this is it's very close to Labourie's original definition of a Anosov representation in the PGL-DR setting. Okay. All right, so if you were like me and you saw this definition, I mean, for maybe years, I was very confused about what this second condition is saying. Okay, so what I'm going to try to do now is I'm going to try to reinterpret this second condition as saying that as saying that this map here, this pair of maps, preserves, like the way that it takes boundary gamma and puts it into GRKRD and GRD minus KRD, it preserves the north-south dynamics on boundary of gamma. Okay, that's what my goal is. Okay, but before I do that, let me make let's make some observations. Okay, these are observations that Labourie made as well. Okay, from this definition. So the first observation is that your representation is PK Anosov, right? If and only if it is PD minus K Anosov. Okay, if and only if. Oh, I forgot to. There's one. Okay, so this is what it means for this to be a PK Anosov representation, right? So more generally, if you take any subset theta inside of delta, okay, then I say that rho is P theta Anosov, right? If it is PK Anosov for all K in theta. Okay? Okay, so the first fact I wrote it halfway just now. So rho is pk Anosov if and only if it is pd minus k Anosov. And of course, if this happens, then this is if and only if it's p k d minus k Anosov. Okay, so in the definition, especially the second part, there's a bit of an asymmetry of k and d minus k, right? This looks like the rows of k and d minus k are different. Okay, but basically the contraction of this bundle is the same thing as expansion of the other. Okay, so there's some playing around you can do, but you can get this fact. Okay, this one and this one is by definition. Okay, but what this tells us is that it's often harmless to assume that my theta is symmetric. Okay, so okay, so this implies that can assume my theta inside of delta is symmetric. Okay, meaning that an integer I is in theta if and only if d minus I is in theta. Okay. Second fact. Okay, it's if you look at this. Let's see. Okay, I'll just write it here. If so, the second fact is that this I don't know if okay, I'll write it there. The maps ck and cd minus k are determined by rho. Okay, so if rho is pk Anosov, okay, then the map ck. Okay, I will just say and ck cd minus k and eta k eta d minus k are continuous transverse rho equivariant. Okay, then they have to be equal.
Don't you need them also to satisfy the contracting chain property?
I don't think so, right? Because if you know that I'm assuming it's pk Anosov already, so you know that one of them really satisfies the contraction property. So, yeah. Okay, so because of this, so these guys here are kind of determined by a representation. So we call these guys the kth limit map of your representation. Yeah. Okay.
So can you explain why these two pairs need not to be contracting?
They are no. So I'm assuming rho is pk Anosov. So you have some contracting. Pretend that this guy is the one that comes from the definition. I just have some other transverse pair, right? So when you apply the flow now, okay. So okay, maybe it might be a bit clearer later because I'm gonna give an idea of a proof later. Okay, so it might be a bit clearer later. Oh shoot. Okay, this is not going well. Yeah, okay, let me pull this a little lower. Okay, the top part is still obscure, but okay.
So the statement was that for theta Anosov, these transverse maps are uniquely determined. That was the statement.
Mm-hmm, mm-hmm, mm-hmm. Okay, and then the last fact. Okay, better. Okay, so the last part of the last observation, okay, is that if rho from gamma to g again is P theta Anosov. Okay, and K and L are in theta. K less than or equals to L. Okay, then for any x in the boundary of gamma, okay, Ck of x is inside of Cl of x. Okay, so this is another consequence of the contraction property. And so this tells you that you can actually combine your limit maps together to get a map into the space of flags. Okay, so this means that you can have, okay, so you can make the map C from the boundary of gamma into what I'm going to call F theta of Rd. Okay, so this is the space of partial flags, right? So if your theta here is I1 to IK, okay, then this space of partial flags is some F, which is a nested sequence of subspaces, one of each of the dimensions that show up here. Okay, so this Fi1 to Fik. Okay, so my notation here is that this is something in the Grassmannian of I1 planes in Rd, and I have just this nested sequence. Okay, so this is, if you want, this is a G mod P theta. Okay, where P theta here is the intersection of the P sub IK, P sub I1 to P sub IK. Okay, let me write it. Okay. Okay, so this is okay. So these are observations that Laborie made. Let me just make sure I didn't miss anything. Oh yeah, some terminology. So this guy here is called the theta limit map. Okay, of rho. Maybe P theta limit map, just to make it consistent. Okay, and its image is the P theta limit set. Of rho gamma, and this is often denoted by lambda theta of rho gamma. Okay? All right, so far just terminology. Okay, so so here's a theorem, and I hope that this theorem help at least make the Laborie's definition a little bit more I guess gives it a bit more geometric meaning. Okay, so so suppose that you have a representation rho from gamma to PGLDR. Okay, and I suppose that it satisfies condition 1 of my definition. Okay, then the following are equivalent. Okay, so first, rho is PK Anosov. Okay, so condition 2 is satisfied. Okay, second, there exists constants, big C and little c, okay, such that for any element gamma and gamma, okay, if you look at the logarithm, I forgot, okay, so maybe I should define some things first. Okay, so if you take any element G in PGLDR, okay, there are a few, okay, so there are a few invariants, natural invariants you can associate to G, okay, namely the eigenvalues and the singular values. Okay, so I'm going to let lambda 1G to lambda DG be the modulus of the eigenvalues, okay, of any linear representative G bar in SL plus minus dr of G. Okay, so eigenvalues here, you means over C, right? So you take the Jordan you put G in G bar, take this linear representative in Jordan normal form, okay, and then the diagonal entries are some complex numbers. You take the modulus, okay. So this doesn't depend on the choice of your G bar, okay, because you're taking there. Okay, so when D is odd, there's one choice. When D is even, there are two, but they're negatives of each other. So it doesn't matter on the choices, okay. Similarly, I can let sigma, okay, and then this thing here actually showed up already. Okay, so secretly this is the Jordan projection. Okay, so I guess it's not secretly, it's kind of obvious the way I said it. Okay, which is okay, so if you define lambda from G to A plus, so A plus in this setting is the set of diagonal matrices, traceless, real value, okay, and the entries are weakly decreasing down the diagonal. Okay, if you look at this, okay, so and when you take G and you send it to the diagonal matrix, which is log of lambda 1 of G to log of lambda D of G, okay, this is the Jordan projection. Okay, and similarly, you can define sigma 1 of G to sigma D of G. Okay, so these are the singular values of the linear representative G bar again. Okay, so what are these singular values? So imagine you have your G bar is a map from RD to RD, right? So this is your G bar. Okay, what you do is you take the unit sphere centered at the origin, okay, inside of RD, and then you apply your linear transformation G bar. Okay? Then what you end up with is some kind of ellipse. Okay? And then now you look at, okay, so first you look at the major axis of this ellipse. The length of this major axis, okay, maybe I should write something. So this is unit sphere centered at the origin. Okay, and then now I look at the major axis, and its length is the first singular value of G. Okay, and then now I take the perpendicular to this major axis. That's going to be a hyperplane. I look at the cross section of my hyperplane with this ellipsoid, and that gives me an ellipsoid of a lower dimension. I look at the major axis there again. Okay, that gives me my second singular value. And you keep going. Okay, so these are the singular values. Okay, and these are really the numbers that show up when you take the Cartan projection. Okay, so if you define sigma from G to A, okay, where you take a G and you send it to log of sigma 1G to log of sigma DG. Okay, this is the Cartan projection. Okay? Okay, so back to the theorem. If you look at the logarithm of the ratio of the k to k plus 1 singular value of rho gamma, okay? This guy here is bounded below by 1 over c times the distance in gamma between the identity and gamma minus little c. Okay, so this is with respect to some word metric you pick on the group. Okay, it doesn't matter which one you choose. Okay. I should point out that there's also an upper bound here. Okay, but this upper bound is true for any representation. You don't need Anosovness for this. Okay. Okay, so this is the second equivalent way to say what Anosovness is. Okay, I should mention that this was in the work of GGKW, and also in Kapovich, Lieb, and Porti, they proved this as well. But actually, they proved something that's much stronger than this, which I'm going to discuss tomorrow. Okay. Then there's also the third part. Okay, there exists some constant c larger than 0, such that if you look at the logarithm of the ratio of the kth to k plus 1 eigenvalues of rho gamma. Okay, this is bounded below by 1 over c times the minimum translation distance of gamma inside of its Cayley graph. Okay, so this, you look at the minimum over all points in gamma, and you look at the distance in gamma between O and gamma times O. Okay, so usually I'm going to abbreviate this thing by L gamma gamma. Okay, the length of gamma. Okay, and this again, you have secretly you have this upper bound again. Okay, up to maybe making your C bigger. Okay. Okay, so this is also GGKW. Okay, so you can see these guys. Okay. Okay, so far nothing tells me anything. I haven't said anything about boundary maps. Okay. Yes. With the existence of limit maps. I'm assuming, yeah, I should mention, yeah, thank you very much. So this again, Cassel-Portree proves something stronger than this, which I will mention tomorrow, okay, about when you remove the existence of limit maps. Yeah.
What is the exception given? Given the finite generation?
No, hyperbolic. I erased it, I think.
Okay.
Yeah, for today, gamma is always a hyperbolic group. Yes. So today, when I define Anosov representations, you always need hyperbolicity. Okay, so I forget which one is. Okay, this one is less important now.
Is this a gamma? Is comparable to the norm of Jordan projection?
The norm of the yeah, but that's you mean in the case when you are Anosov. In general, I mean, you take some arbitrary representation. There's no reason for that. Yeah, but in the case when you're Anosov, then yes, you can get it from this.
Okay. Right.
Yeah.
Right.
To rephrase, either 2 or 3 implies that the orbit maps quasi-isometric embedding.
That's
Just a
right.
way of rephrasing.
That's right. So
Guillaume's question.
yeah, that's right. Okay, but again, I'll make that more explicit tomorrow. Okay, when I'm actually going to focus more on the geometry of the symmetric space. Okay. Fourth part of this theorem. Okay. So I don't know. This is like okay. So this is really the part that I want to focus on, because this tells me something about this allows me to interpret Labrouille's definition as a property of the boundary maps. Okay, so if you look at the boundary map C, the map C from the boundary of gamma to this flag manifold, okay, this map here is strongly dynamics preserving. Okay, and what does this mean? This means that if you have a sequence gamma I inside of gamma, such that gamma I times A, gamma I converges to A in the boundary of gamma, and gamma I inverse converges to B in the boundary of gamma, okay, then rho gamma I applied to F converges to C of A for any F in Fk d minus k RD. such that F is transverse to CB. Okay, so the picture you should have something like this. Okay, so here, this is the picture in your group, which I drew yesterday, right? These group elements, gamma i's that converge to A, and the gamma I inverses that converge to B. Okay, and then you apply when you apply the C. Okay, so then this is now a picture inside of the flag manifold. Okay, you have B, which is some flag. Okay, and then you have A, which is some flag. Okay, and you take any flag, any other flag that's transverse to this guy. So this is supposed to be CB and CA. So maybe something like this, and you keep applying your group element, you converge to CA. Okay, so this is what I mean when I say that the north-south dynamics in the boundary of the group is transferred into the flag manifold. All right, so this last characterization, I mean, this terminology, I think it first showed up in my paper with Dick and Andy. But really it comes from the work of Suvala. So he characterized Anosov representations using this thing called the PK Cartan property. Okay, and modulo a linear algebra lemma, you can get this from that characterization. Okay, so maybe I'll attribute this to Costas. Okay, maybe I'll write on our names here as well. Okay. Okay, so this is how I like to think about this property. What's next? Okay, so now I would like to give an idea of a proof. So in this theorem, so parts 2, 3, and 4, they all involve the group elements, right? Okay, singular values, eigenvalues, or how it acts on the boundary. Okay, but at least when I first learned this thing, I was maybe it's not so obvious if you're not familiar with this, how you get from 1 to maybe 2. Okay, how you go from this contraction property of the flow, right, into something about the singular values of the group element. Okay, so I'm going to try to give a proof by picture. So I'm not going to write any works. Okay, a proof by picture, but I need to make some assumptions. Okay, so this is a proof of maybe 1 implies 2 by picture. Okay, maybe I won't say proof. Maybe proof in parentheses. Okay. So I'm going to, because I want to draw pictures only, I'm going to assume that my D is 2. Okay, but once you understand this, I don't think it's that much harder to do it for higher dimensions as well. Okay, so, first I pick a compact set. My compact set K inside of my flow space, inside of my U gamma. Okay, and with the property that the translates of the compact set under gamma covers the entire space. Okay. Gamma times K equals to U gamma. Okay. Now I pick my, so I want to show something, I want to show this, right? So I pick my gamma, okay, and I apply my gamma to this K. So I get another compact piece here, which is gamma K. Okay? So what you want to, first thing you want to do is you want to say that you can find some point V in your flow space so that as you flow for positive time far enough, you can get to this set here. Okay? So zoom, you flow. Okay, eventually you end up here. So this is some phi TV for some positive T. Okay? So, and then so you have to show that you can do that. And then you can, and then you need to, and then when this happens, the parameter T here, right, is comparable to the length of gamma in the translation distance of gamma inside of the Cayley graph. Okay, so you have to show also that T, this T here, right, is comparable, means up to uniform multiplicative and additive constants. Okay, depending on the size of K. Okay, it's comparable to the distance in gamma between the identity and gamma. Okay? So this is what allows you to go from, you know, the t parameter in the definition, in the flow definition, to this distance here, this one. Okay? All right. So now, now what do you do? Now I'm going to look at the fibers of my bundle. Okay? So I have my d equals to 2. So I have this R2 trivial R2 bundle over U gamma, right? So above each point I have a plane, right? I have this plane here. Okay, so I'm only interested in 3 points. So this point, and the translate of V by gamma. Okay, so this is gamma V. Okay, so this is the fiber above these 3 points. Okay, now by assumption, my Anosov assumption tells me that I have a splitting of the bundle. Okay, so above here I have this splitting. So this is maybe you can think of this as C1 of V minus. And this is C1 of V plus. The vertical one is C1 of V plus. Okay? And then this splitting is flow invariant. Okay, so all the R2s in this picture, they are all identified, right? This is when the trivial bundle. Okay? But this splitting is flow invariant. So as I flow, I see the same picture here again. Okay? Okay. Now at this point, I still have a splitting, but the splitting will be different. Okay. So at this point, I have some splitting like this. Okay, and so maybe this one is C1 of gamma V minus, and this is C1 of gamma V plus. Okay. So I mean these two things might be very different, right? Okay, what else do I have, right? So I have a norm on, okay, so I look at the Hom bundle, right? In the definition, I have to look at the Hom bundle, the homomorphisms from C1V minus C1V plus, right? This is a plane, so the Hom bundle is a one-dimensional vector space. And if I want to specify a norm there, I just need to tell you what is the norm 1 vector, right? So my norm, I can think of it as choosing a norm 1 vector in the Hom bundle, or if I look at its graph, it's just choosing a line here. Okay, so I have this line, okay, that basically tells me what is my norm 1 vector. And I have this line everywhere, okay? And this one is gamma invariant under the gamma action. Okay? Now, I pick my f. I pick my vector f in this above V. Okay, so this f is something in the Hom bundle again. Remember, here really I'm drawing the graph of f. Okay? And as I flow, you know, the way that I define my flow, it doesn't change. Okay, so I still have f here. Same f as we had, okay? But I have contraction now. As I flow, my norms are contracting. So what does that mean? That means that in this picture, right, the norm, the unit norm vector is very steep, right? You are contracting exponentially. So here, this is your norm. Okay, and you can control, I mean, the norm is really the slope, right? And you know, and you have bounds on how gentle the slope can be, because and it's in terms entirely of t, right? Because you flow, you must contract exponentially. Okay. Now, if you look at let's go back to the base k. Okay. If you take any 2 points in the base, because this is compact, the norms. If you look at the vector spaces above them, the norms there, norms of the Hom bundles, they're all they're bi-Lipschitz. There's some uniform constant c where they're all bi-Lipschitz to each other. The norms are gamma invariant, so the same thing happens here in this picture as well. Okay, so if you know that this norm is really, really big, I mean this vector here is really steep, then in this picture, it also has, you have a bound on how gentle it can be as well. So this guy also must be steep. Okay? All right, so now the last part, okay, okay, so this is how you get the singular values, okay? So now instead of this original picture, I pick a vector in CV minus and a vector, what color have I not used? Green. Okay, in CV plus, this was bad. Maybe this one. Okay, better. Okay, and I pick these two vectors so that the sum of them gives you the direction of the norm vector. Okay, so if you add them up, you get the direction of this vector that gives you the norm 1 vector. Okay, now when you apply rho gamma to these two vectors, what happens? So this C1 V minus gets sent to C1 of gamma V minus, right? So this purple vector gets sent to some purple vector inside of this line. Okay, maybe I should make this a lot steeper to illustrate my point. Okay, sorry about this. Okay, so my purple vector gets sent to some vector inside of this line, and this brown vector gets sent to some vector inside of this line. Okay, but also because my norms are gamma invariant, the sum of these two vectors still must give me the norm 1 vector in the Horn bundle. So when you sum these two things up, you must give me the direction vector of this guy as well. Okay, but now you can see where the singular values come in, because now your group element rho gamma, you see it has to take this brown vector and you have control on what's the minimum amount. Okay, if you look at the ratio of these two lengths, right, and you map them over, you have control on the maximum stretch, I mean the minimum amount of the max stretch and the maximum amount of the min stretch. Okay, and this is where you pick up the singular value of the group element. Okay? Okay. Okay, I don't know how many people I lost, but I'm going to cut my losses and move on. Okay. Oh, shoot. Okay, this is kind of... Okay, so that's this. One more. Okay, let me give you one more proposition before we start. I will call this a theorem. Maybe it's not obvious. Okay. So this theorem, I just want to state this theorem to illustrate the usefulness of Labourie's original definition, even though the other versions of it is easier to state. Okay. So using Labourie's definition, you can prove results like this. Okay, or not. Maybe you do. Okay, the first one is is from Labourie's definition. Okay, so the set of p theta Anosov representations. Okay, inside of the space of homomorphisms from gamma to G is open. So you have the stability of this kind of guys. You can perturb this, which is what we want. Okay? So this is due to Labourie. Okay? Second, you can show that if you have an analytic, so if I call this set here A theta, and you have this analytic family inside of A theta. Okay, then if you pick any point x in the boundary of gamma, okay, the map from M to the flag manifold, okay, where if you take you take a representation rho, okay, and you send it to C rho of x. So C rho here is just the limit map for your representation, the theta limit map for your representation rho. This guy here is analytic. Okay, and this is in BCLS. Okay. And then third statement is if the map C rho. Okay, so if rho is p theta Anosov, okay, then C rho from boundary of gamma to the flag manifold is Herder continuous. Okay, and the Herder constants can be made to be uniformly, locally uniform. On A theta as well. Okay, and I mean, these things are they play an important role in BCRS construction of pressure metrics on the space of Anosov representations. Okay, and I think the easiest way to get this kind of results is you have to use the flow definition of Labrie and work from there. Okay, so I have a bit of time left. So the next thing I want to do, so now we've done our definition, I want to look at examples. Okay? So I'll probably not be able to cover all the examples I want to talk about today, but I want to, maybe I can do a few of them. Okay, so first, also example 0 is, okay, convex co-compact subgroups. Okay, in rank 1 Lie groups. Okay, so in our case is PGL2 when D equals 2. That's the only rank 1 guy in our family. Okay. So the second example are the Hitchin representations. So they showed up in our talk in the talk earlier today in what was it? Hitchin representations. Yes. So all right. So Hitchin representations, right? Okay, so these were not defined, that's why I'm going to define them now. So what you do, okay, so I'm going to let gamma be the fundamental group of S. Okay, where S here is a closed oriented surface. Of genus at least 2. Okay. Okay, then I'm going to let iota D from SL2R to SLDR be an irreducible representation. Okay, so these are unique up to conjugation. Okay, and if you, because I'm working in PGLDR, if you want, you can just projectivize it and put it inside of PGLDR. Okay, so this is my iota D. Okay, so a definition, a representation. Okay, so a representation rho from gamma to PGLDR G. Okay, is Hitchin if it can be continuously deformed in the space of homomorphisms from gamma to G, in the space of homomorphisms from gamma to G, okay, to something of the form iota D compose J, okay, where J from gamma into SL2R is discrete and faithful. Okay, so these form entire connected components of this space, right? Okay, and these Hitchin representations, really the first kind of when Labrie first defined his notion of Anosov representations, right, to study these guys. Okay, and so his theorem is that every Hitchin representation is P delta Anosov. Okay. So So if you start with iota d compose J and you put, okay, so verifying that this guy is P delta Anosov is not that hard. Okay, and so if you perturb it a little bit on a small neighborhood of things of this form, you can show that, you know that those are P delta Anosov by stability. Okay, but what Labrie shows is no matter how far you deform from this, you still stay P delta Anosov. So these form entire connected components of the space of homomorphisms that are made up of P delta Anosov representations. Okay, and this is really the starting point of higher technical theory. And today, nowadays, there are much more of these kind of representations with this feature that people study. They call them data positive representations. And I think in a soon to appear preprint, not by me, by other people, they can also show that these data positive representations, they are all data Anosov as well. Okay. Okay, so this example one. I want to do one more example. Okay, so these are the bubble examples. Okay, so what I'm gonna do is I'm gonna look at this representation that I call iota d plus 1. So this goes from SL2 to SLD plus 1R, SL2D plus 1R, right? Where you take your G and you send it to iota dg, iota d plus 1 G, like this. Okay. Okay, and then the fact here, okay, is that
just iota d plus 1, right?
yeah, sorry, you're right. Thank you. Okay, and then the fact here is that if J from gamma to SL2R, okay, if you want to make it land in PGL-DR, you just projectivize again, 2D plus 1R. Okay, so if J from gamma to SL2R is discrete faithful, okay, then iota d plus 1 composed with J is P delta Anosov as well. Okay, and so any small perturbation of them is also P delta Anosov. So in the case when d equals to 1, so there was a paper written by Babo where he showed this in the case of d equals to 1. Okay, but that was in the early days of Anosov representations. Nowadays, it's much easier to see why something like this is true. Okay.
But
okay.
It's not like the whole connected component.
No. So yeah. So now, yeah, only a small perturbation of only a small neighborhood. So that's very. So these are not examples of what people study in higher technical theory. Okay.
So it is known. I mean, you have a non-positive representation in the same connected component. Or?
Yeah, I think so, because in the like you have the components of, at least in d equals to 1. SL3, I think there are 3 connected components. One of them, so yeah, so I think these guys live in the identity component.
I see.
I think something like that. I'm not sure. But there's some argument. There's some. It's not. They don't form entire connected components.
Really simple way to see it is you blow up the first term by a factor and the other term by the corresponding factor. Then eventually you're going to stop being loxodromic.
Right. Okay.
And then you can see just even within the reducible locus the details.
Yeah. That's right.
So it's really
That's right. Yeah. Okay. All right. So maybe I'll just make one last statement, which is so right now I've described in both cases gamma is a surface group, and I've produced for you P delta Anosov representations, right? So as far as I know, these are the only 2 ways to construct P delta Anosov representation of surface groups into PGL-DR. So the question now is, are these all of them? Are there more? Okay, I don't think that's no. Okay, so
you can maybe replace gamma by convex compact and then use character.
no. So if you have free group, you have much more. If you use a free group, you can play ping pong. There's much more. But closed surface groups. Okay, so let me just stop here. Thanks.
Questions for Tengren?
Are you going to also talk about relative Anosov representation or not?
In my original plan, yes, but I don't think I'm going to get there. I'm sorry. But I think maybe some other people might, yeah.
Other questions?
Yeah, I have a question. What do you think about the question you just posed at the end there?
So I would say that.
Are there other ways to make them?
So when d equals to 1, I'm willing to make that a conjecture, that there are no others.
Okay.
But I can't really, when d is bigger than 1, so these bubble examples, they only show up in odd dimensions. So maybe the easier question in some, because the problem is when you exhibit a representation, right, even if it's Anosov, like how do I show that it's bubble? That's quite difficult. Right, how do I find a path of deformations to get to a reducible one, right? But in the even dimension case, the conjecture the question just becomes, are there p delta Anosov representations that are not Hitchin?
Yeah.
Right, so that might be, I don't know. Yeah.
I see. So you're saying in this bubble example, d plus 1 is important. If you do d, then it doesn't
No,
work.
it doesn't work. Yeah, it's not. Because you have repetition of eigenvalues. So when you look at the irreducible guy, right?
Yeah.
What are the so if you take like a diagonal element.
Just if you look at SL4, right? Like, okay, if you put this SL2, SL2 there.
So then if you do this, you have repetition of the eigenvalues. So you don't have eigenvalue gaps.
I see.
You need eigenvalue gap at every adjacent pair of
But
eigenvalues.
maybe then it is a p alpha 1 and also.
But I36 would also work, for instance, right?
3-6?
Yeah, 36 will also work.
No. 3-6?
I think so.
Oh yeah, you're right. You're right. Sorry.
If it's odd, take it odd.
Oh, okay, you're right.
You
Yeah.
get lambda to odd powers, and then the even irreducible representations, you get lambda to even powers.
Yeah.
So you always have a gap of at least
Right.
lambda.
Right.
For lambda is the original
Yeah, sorry.
value.
So it's
Yeah.
not Anosov for minimal parabolic, but it's Anosov for some parabolic, right?
Yeah, but the question is really about minimum max the Borel, the minimal parabolic. Yeah.
I think you mean the surface group representations.
Yeah, surface group representative, not free group. Yeah.
I think it'll still be Borel and Anosov. Yeah, all the gaps. You won't have any eigenvalue agreement between if you do I36.
Yeah, I guess we're just talking about this example.
This one.
Oh, yeah.
This is P2 and also. Yeah.
If you do 2-2, you're in trouble, yeah.
Yeah.
Maybe, so this means maybe
Anytime you do
change
even, you're in trouble.
basically you can change the conjecture to allow also for
Yeah. So DL where one of them is even, one of them is odd. That's right. Yeah. D prime. Yeah.
Jack, do you have a question?
No, it's more of a comment. Just a question about in which component it goes when d is equal to 1. So that's the original case of Barbeau. It depends on the genus, on which component it goes. It's either on the component of the trivial representation or not, depending on the parity of the genus.
Okay.
And one other reason to know that you can deform them to non-Anosov is that in each of these two components that are not the each in one, you have representation in compact groups. So, thank you.
Okay.
And your question, like one of the questions it uses is, do you have Anosov representation in each of the three components for SL3? Because, well, it's formulation or more or less.
Yeah.
Very natural question. Yeah. Okay, let's thank Tengren again for a very nice talk.